2, ready, and hey, how's it going, everybody? Brad the Guitologist here. In this video, we're going to take a look at this 1960s Gibson Skylark with tremolo. This is GA-5T is the model on this. You can see there the little Gibson coat of arms. Got a power switch. I've got a jewel light, 1 amp fuse, loudness and frequency of the tremolo, and 2 inputs. Pretty simple on the front. We do have really nice grill on this. It's in good shape. I've got some kind of protrusion down here, so something is actually stuck, it looks like, maybe between the grill cloth and the baffle. So we'll see maybe if we can pull that out of there, figure out what that is. I might have to remove the speaker to get to it. But let's go ahead and turn this thing around and we'll examine it a little further. I do notice that the handle is nice and intact. This is a leather handle that often is missing. I've had some of these before that were missing. I've done several of these on the channel before, so this is not it's not going to be a new amp to us here, but it's possible we might do a couple different things and experiment with some different values on some of the coupling capacitors perhaps, and try to maximize the tone of one of these. So if that sounds like something you'd be interested in, stick around and let's go ahead and turn this thing around and get into it. Okay, so here is the rear of the amp. We can see down here the Gibson logo is intact. Unfortunately, it's also covering the speaker code, so we won't be able to get the date of the unit off the speaker code, but we will be able to probably get it off of some transformers and some other stuff. We do have a 3-prong cord already on it, so we will check the way in which that was wired. The baffle is screwed in. We'll be able to remove it fairly easily once we get the chassis out. The chassis, in order to get it out, we have to first get the back door off, and there are 4 screws that we can see here, but there are also inside, there's some hidden screws on these, and if you unscrew these 4 screws and you start to remove one of these, you're wondering why the hell you can't get it off. That's why. There are 2 screws underneath. There's one right here and one over here. This actually screws to the chassis also. There's a lower lip of the chassis, and you have these bolts that pass through the chassis, and they have nuts on the other side, so we'll have to remove those nuts as well. So let's go ahead and remove these screws, remove those nuts, and we'll pull this back door off and we'll get a look inside this thing. Okay, I don't know what size these nuts are, but I think they're fairly large, the best I could remember. 3/8 probably. Yep, they're 3/8. Am I going to be able to... I need a deeper socket than that, don't I? Yeah. I need a deeper socket, or a... I'm just going to have to use an adjustable wrench instead, because it's not... A deeper socket is going to go too far back in there. I won't be able to get it. I won't be able to make that work. I think they put those on there to keep this back door from rattling against the back lip of the chassis. It also serves to hold the chassis in the amp so that it doesn't rattle around. I think it's actually the only thing securing the chassis. So the back door is secured to the rest of the cabinet, and the chassis is actually only secured to the back door. So without it being secured to the back door, it's secured to nothing else. So the last one that I had, I think, was actually missing these, and I had to replace them because somebody had just said screw it and left them out or forgot them. This amp probably has one of the Sprague couplet devices in here that basically does some tone shaping in the amp, and usually it's a good candidate for replacement. Yep, it absolutely does. Looks like this thing might be all original. But you can see here on the back door, you can see what I mean about these bolts. So there are a couple bolts, and they have to be countersunk in here on this side because they're flush. So that's what secures the chassis in this amp. And without it, it should just push right out the front. Best I remember too, you actually have to remove the baffle to get this amp out because it has to slide forward, and it can't slide forward obviously, but with all this stuff hanging down, you have to remove the baffle also. So let's go ahead and we'll take the baffle out, and then we'll get this thing out. But you can see here already what I'm looking at. We've got an old Astron multi-section cap over here. That's a 20 and 20. It probably has a date code somewhere on it, I would imagine. We can probably get off of it. They usually don't stand up very well. That will get replaced. This big one here will get replaced as well. It probably also has a date code on it. 100% original, I would say, inside of this. You can see all the original. There's a little black, that should be a Sprague capacitor right there. Probably a bypass cap on one of the stages. We've got a Bumblebee cap right there. That's probably going to have to go. Those almost never are good in amplifiers. They work okay in just low voltage tone circuits, but they do not work or hold up inside of amplifiers or anywhere where there's high voltage present. And that will need to go for sure. That Black Beauty right there might have held up a little bit better, but it still probably needs to go. We will replace it as well. There's another Sprague Black Beauty over there that probably needs to go. Looks like there's another one tucked back in there that will need to go. So we're going to overhaul this amp. This is not going to be a thing where we try to sympathetically leave the stuff that's still working, because these Spragues right here, like I said, although they might technically still function in this amp, being the age that they are right now, you know, they're going on, what, 60 years old? That's not the kind of thing you want to leave in an amplifier. It really isn't. And since I'm already in here anyway, and I'm going to have to replace these electrolytics, it makes no sense to leave those in the amp at this stage. Now that Sprague couplet right back there, that thing, that certainly needs to go if you want this thing to really sound its best. Now I could do, I guess, a sympathetic repair or restoration of the electronic circuit to get it to functional condition, but it's not what I would consider worthy of being relied upon, because you're just going to be leaving in a lot of stuff that really needs to come out. I will make sure, you know, obviously before I do anything, and make sure the customer's okay with this, because this is not my amp. This was shipped to me by someone. I think the fellow bought it off of eBay and had it sent to me. Best of my recollection, I'll have to look that up, but I'm not sure. So he might not have even seen it yet. So we'll have to discuss what his goal is with this, what he wants to do. I would say preservation of it in its current state is not a good idea. It's best to go ahead and make this a functional amp, make it a playable amp, you know, something that he can actually jam through instead of something he has to pussyfoot around with. Let's contact him and we'll see if that's what he wants to do, if that's what he has in mind, and we'll kind of go from there. In the meantime, we'll go ahead and remove this front baffle, and it looks to me like probably the thing that I was seeing poking out the front was probably the other side of that bolt right there is what was poking out the front on the front grille. I'm pretty sure it probably, yep, definitely is. Seems like things can never really be easy. I've got one stubborn nut down here, so I'm gonna WD-40 that. Let's see if I can't get it loosened up a little better. I might have to actually screw it back in and then back it out again so I can get more lubricant to it. We're definitely hitting something, some kind of rusty spot or a burr or something on there. It doesn't want to come out. Went ahead and hit this other one here too with WD-40. I think I'm gonna go ahead and might as well hit the rest of these with a little bit of it. Easy peasy on that one. This is the only one that's giving me fits, and it definitely looks like somebody at some point either did take this out or tried to take it out and got stuck and couldn't go any further or something, because like I said, I've got that bolt kind of protruding out the front of this thing. All right, the baffle is ready to come out, but we have to desolder the speaker. You know what? Hell with that. I've got plenty of lead there. I'm just gonna chop them. The other cool addition to an amp like this would be a speaker jack. If we installed a speaker jack here, an output jack, he'd be able to unhook this internal speaker, which frankly is a little bit on the weak side. These are not very efficient speakers. Look at the size of the magnet on this. I mean, you're not going to be doing much with this other than probably recording. You know, I mean, they get loud enough for bedroom use, for practice and recording, which is fine, you know, for those applications. But, you know, if you wanted to set this thing up on a stool at a gig and mic it up, it might be nicer to have a better speaker cabinet. And even for recording, it might be nice to have options. We'll get a hold of him and see what his goals are with this. If his goals are to have a collector's piece or something like that, then maybe we'll just end up doing the minimum. But if his goal is to have something that is going to sound its absolute best that it possibly can and be as flexible as it possibly can be, then we may, you know, do some light modifications, including an output jack. Okay, so here we've got our first look at the underside of the chassis, so we might be able to date this thing. It's going to be somewhere between, I think it's a 63 or 64, and it's a 64. Right there, 996-6410, so it's the 10th week of 1964, the TF5AP, that's the transformer code. The output transformer, I'm sure is original also. I can pretty much conclude that just by looking at it. Upside down we read 549-6422, so it's 1964, the 22nd week of that year for that output transformer. On our rectifier tube we have a, what is this? What is that? It's a 6X4. These all look like they're Sylvania tubes. Probably are all original tubes. 6 AQ5As on the output. We have a pair of those. I like the sounds of 6 AQ5s. Cool little tubes. They are more or less a 6V6 equivalent in a 7-pin miniature tube. We have two 6 EU7s in this amp also. One of it, which at least is Sylvania, and this one is an RCA. Great tubes. The cool thing about these is that a V1 is actually isolated from the rest of the chassis. The rubber mounts for the isolation are actually really supple and really nice, so they're still in really good shape actually. That isolation right there, of course, is to help dampen down any vibrations that might enter in to the tube and cause microphonic feedback. So that's cool, a good design feature. Just overall, really well-built amps, Gibson amps of this era. The only complaint with them really is that they did not manage to maximize what they had here in the design so that they were able to, you know, do what we really want vintage tube amps to do, which is break up and be gnarly and bark back at us. You know, when we hit a chord or a note really hard, we want it to go into overdrive. And I think at this time, Gibson was really trying to keep things clean as possible, and that's one of the main reasons why they included these little Sprague couplets in here between a couple of the stages to try to shape the tone, and really it just ends up killing the tone as far as I'm concerned, and as far as a lot of other people are concerned too, because it's a very common mod to remove those and to replace it with just a standard value coupling capacitor. Okay, on this baffle screw protrusion right here that we have going on, like I said, you can see the bump here. So this bolt is protruding out the other side. It really shouldn't be doing that. It should be down inside of a countersunk little area right there. But I don't know if this thing has got spikes on it and it got pushed out and then turned so the spikes aren't lining up with their holes, or what the deal is. A couple ways we could do this. We could pop the grill cloth off and kind of peel back just this corner and fix it that way. But I think the approach I'm going to take, so that I don't have to pop all these staples out, we'll just screw this in. Seems to be working. There we go. Sweet. Okay, so that pulled that all the way back in. So now that head of that bolt is seated down in the countersunk area where it's supposed to be. So that's much better right there. Nice and flush. I'm going to put the chassis and this baffle back in on second thought because we'll just hook up the speaker so we can get a sound test of what it sounds like right now. Okay, we got the amp plugged into the Variac. The power switch is on, so we'll go ahead and start dialing it up slowly. It's definitely drawing something, so we got 3.4 watts power being consumed somewhere. With as old as the capacitors are in this amp, you know, I'm just going to take it easy on this initial fire up because, like I said, this is only for curiosity purposes to see where the thing is tonally right now before we do any kind of work or modifications to it. Okay, so we're 57 volts in and we've got a lot of noise. So we're drawing 6.9 watts. We're not bad on the wattage. I mean, it's not like we've got a capacitor that's shorted, but we definitely have a capacitor that is not healthy. Gonna go ahead and dial it up just a little bit more and see what happens. But right now, I mean, this is completely useless. This would not be a usable amplifier in its current state. I can hear the tremolo trying to work, but it's not doing a very good job of working. So this is definitely a classic case of needing some electrolytic capacitors very, very badly, which is what I kind of expected. But I was hoping we would at least be able to see what the original tone is of one of these Skylarks, because the idea was to show you what it sounds like before any kind of modifications. So I just emailed the customer. He emailed me back and informed me that, you know, the reason he bought this amp was because he saw a Rhett Scholl video that showcased a Skylark amplifier. He said he saw a couple of my videos as well, but he said he wanted it because it seemed capable of sparkling cleans. I watched the Rhett Scholl video. He didn't open the amp, so I don't know what the hell's inside his amp. I don't know how many videos of amplifiers can be made without opening an amp and showing the guts of it, but you know, he's got 500,000 views on that one, so I'm doing something wrong by showing the guts of these amplifiers. You know, I should just go for style over substance, because I can't fathom why a video like that had 500,000 views. He didn't show the inside of the amp. He played the amp with a bunch of pedals. Granted, it sounded good, you know, and I appreciate some of the things he had to say in the video, but holy shit, can we not have a more discerning viewing public? But anyway, I'm gonna basically do this the way I've done Skylarks in the past. We're gonna remove this couplet up here, replace all of the capacitors, including the coupling caps. First thing I'm going to do is go ahead and remove the death cap over here, and we also are going to have to we're also going to have to redo this power circuit where the line comes in. There is the power cord itself. There's no retainer on the cord here at the chassis. There is a retainer that goes on the side of the cabinet, so it's not that big of a deal, but I am going to go ahead and I'm going to put a couple of zip ties on this just to hold this in place so it can't move in or out. Okay, that's just going to keep that from being pulled out any. Like I said, it has a retainer on the side of the cabinet anyway, so it's not that huge of a deal. Also, this is not really wired correctly. What I want to do is come with the hot wire into the tip of the fuse, which is correct. Then I'll come from the sleeve of the fuse over to the switch, out of the switch through the transformer and then back out of the transformer to the other side. Wait for that to warm up. I'm gonna go ahead and clean the pots. Go ahead and clean the sockets as well, the tube sockets. Boy, that was barely on there. This one's correct. This one has to go. We're just going to wire in a way that's a little more safe. Back in the old days, a lot of times they would have the fuse on one side of the transformer and they would have the switch on the other side of the transformer. The problem with that is if there's some sort of short in the transformer, you can't turn off the amp and cut power to the transformer to prevent the short. Now you do have a fuse that should in such situations blow, but if somebody's put a huge fuse in there, then it might not blow and it would take out the transformer. So you want to be able to switch the thing off, ideally. But also, if there's a short in the power switch, which could possibly happen because it's a mechanical power switch, there are things inside of a power switch that could fail. And if you have the power switch before your fuse isn't going to do you any good. You'll be relying entirely on the house breaker system to break that current if there's some sort of problem in the power switch. So the least amount of components between the fuse holder and the power is really best. That's why I put the fuse first. It's generally recommended now with most wiring schemes that you do put the fuse first and then go to the switch. There are some other amp techs who obviously disagree, and that's okay. I used to do it with the switch first, but I stopped doing it that way out of consideration for having a fuse in as many situations as possible where a short might occur. That's my thinking on that. That's also the thinking of, I believe, Underwriters Laboratories and also the CE, the European system. They also recommend this as well, I believe. So at least until somebody is able to convince me otherwise, this is the way I'll continue to do it. Okay, so to delve into this just a little bit further, because I've seen so much disagreement all over this subject, even amongst competent technicians, I thought I would show you the reasons behind why I do it the way I do it. If we look at the definition for what constitutes low voltage under the IEC, that's the International Electrotechnical Commission. It defines low voltages as being between 50 and 1,000 volts RMS. And if we look at the international standard, the IEC number 60947-3 for low voltage switch gear and control gear, we could see down here on this table the making and breaking of current. We could see a switch fuse circuit right here, and we see that the fuse is coming before the switch in pretty much all of these cases. They're putting the fuse before the switch, and indeed, if we look at some of the actual combinations of IEC power socket, fuse, and switch, some of these combinations, if we look at this, here's the hot right here. And if we flip this thing over, so the hot is here. So the hot is actually coming in and then jumping directly up to the fuse holder. So it goes hot to fuse and then over here to switch. So that is why I do it the way I do it. I'm not saying everybody necessarily should do it that way, but to me this seems like the approach that offers the most benefits for the least drawbacks. So what we're going to have to do now is we come out of this sleeve, we go over to the switch, and then on the other side of the switch, of course, it'll go through the transformer. Coming out of the transformer, that will go to our return or our neutral. So I'm making my way through the rewiring of this amp. I kind of discovered something, a new technique possibly for discovering bad solder joints. There is a solder joint that I have not fully soldered up yet, and I want to show you something. So if I come over here and literally if I flick any one of these connections, it almost gives me a note, and it's real solid. That one right there is starting to sound a little bit trashy, as if it's got almost a snare drum effect. But then listen to this. You see how trashy that sounds? Now the reason that connection sounds trashy is not because of this connection or this connection. It sounds trashy because I haven't yet soldered on this connection right here, and that's what's making the trashy sound when I flick that connection. Now if that wasn't like that, I'm going to put my finger on that. Now I flick the connection and listen. Hear how it sounds nice and solid? Anyway, I just thought that was kind of interesting. I haven't done any modifications yet. We're going to start at the input. I have a bias resistor here and a bypass capacitor that are basically hooked, married together more or less. I want to see first where this first stage is biased. I want to see if I can squeeze any more juice out of this first stage. And to do that, I'm going to use my resistance box. We're going to switch through a couple of different resistances. We will start at the resistance that is stock for the amplifier, which is 1.5K, and then we will kind of go up and down from there to see if we can improve it. Okay, so we have a signal generator generating a 1 kilohertz sine wave, putting it in the input of the amplifier. We're going to dial it up. I've got my bench test speaker out here, so you'll be able to actually hear the sine wave as we dial this up. Right now, like I said, we're at 40 volts. And we've got 67 volts right here at this first node. And we're about halfway up now, about 65 volts. I can hear some noise coming through the speaker now. Dial it up just a little bit more. What's funny is I've got the volume turned all the way down and I can still hear it. Oh, I know what the problem is. Let's dial that back down. Okay, so everything was actually looking pretty good right there, but I want to dial that back down because I unhooked the coupling cap, and the only the sound that we were hearing right there was being induced somewhere into the circuit, so it wasn't actually coming through. Probably wasn't coming through the input. It was being induced somehow. Okay, so that coupling capacitor is tacked back on there. So now we should get something. Okay, so we do have sound, but let's go ahead and we'll test out and see if we can get more out of this first stage. Just put it about right there for a second. Okay, so 470 on that is actually the loudest so far, but let's go ahead and dial it all the way up because we won't really know anything unless it's dialed all the way up. We don't have the buzz anymore. The buzz is gone, so we've taken care of that part of it. That's the magic of replacing capacitors. So let's go ahead and dial it on up. Stop about right there, about 116 volts or so. I think I might go with a 680 ohm resistor on that first stage right there, and we might bypass it with something like a 10. It originally was bypassed with a 20 microfarad, but I think I want to bypass it a little bit lower because we're going to make up for that loss of bass with some larger value coupling caps a little further down the line. Okay, going through this amp, I have noticed a number of things that probably should be done with this that I have not done in any of my previous modifications on this model amp. One of the things I'm going to do, I'm going to change this 500K pot to a 1 meg pot, and that's going to bring the gain or impedance of that particular stage a little bit more in line with what we see in a Fender Princeton, for instance, which this amp is actually remarkably similar to. If we go with the idea that a 6AQ5 output tube is similar to the 6V6. If we put the two schematics side by side for the Princeton and for this amplifier, you should see some similarities right away. First of all, we've got the same number of tubes, so we have two preamp tubes that are very similar, the 6EU7 and the 12AX7. Pretty much the only difference between the 12AX7 and the 6EU7 is the fact that the 6EU7 has a slightly different pinout. The heaters are on different pins, but other than that, and the fact that it does not have a 12-volt option, so there's no center tap for the heater, the 6EU7 is actually remarkably similar to the 12AX7, and the 7025. Given that, we can see that it has the same number of preamp stages, it has the same type of phase inverter, into two 6AQ5s for the GA-5T and two 6V6s for the Princeton, which are identical in their behavior when the 6AQ5 is operated within its design parameters. So the only real difference would be the type of rectifier that's used, the 6X4, which I haven't looked at the spec sheet for 6X4 to compare it to like a GZ34, for instance. For the 6X4, there's not going to be as much voltage there, but this is going to be very much like a Fender Princeton without the tone stack. So yeah, what we're going to have to do here, like I said, I'm going to change this pot to a 1 meg pot, but we may have to do some slight modifications and shaping to get that to work properly with the 1 meg, but we'll see. So the first thing we want to do is pull the knob off of this, and I'll show you something about these knobs. These are pretty much impossible to find now. If you lose one of these knobs off of a Gibson amp, you won't find another one. However, if you turn it over, you look real closely at these knobs, you'll see that there are some numbers there that are kind of latent numbers. This is kind of the top hat knob that's used on some models of guitar. So what you can do is you can get a reproduction of this. You can repaint the chrome, and you can actually come around here and you can paint in the numbers. You can scrape out, if there's paint in the numbers already, you can scrape that out and paint that black so that you'll get the full black skirting around. And then you can recreate this knob, even though it is not something that is reissued today. You can recreate it out of something that exists. So okay, skipping forward just a little bit, I've been doing some modifications on this thing so far, and I've got it sounding pretty smoking, but I want to show you what I've been doing so far. First thing I did was replaced the 500K pot with a 1 meg pot. Now, this is a little bit too much. I'll show you what I mean here in just a second, but I think I can adjust that by changing the bypass capacitor on this first stage. Change the bias on that first stage. It was a 1.5. I cut that in half down to a 750 ohm. As you can see right there, that bypass cap going around it is the one I'm probably going to change here in a second. That 0.02 capacitor right there is the coupling cap coming out of that first stage going into the volume control. Now that is where the network was. This Sprague couplet network was located before. And this is basically just a series of resistors and capacitors that shape the tone. It's basically a tone shaping network. I call it a tone sucking network because on the other side of this, your volume really is severely diminished by all the shaping. It takes out a lot of frequencies and accentuates other frequencies, and basically that was done at the whims of Gibson engineers at the time who were trying to keep things clean. They were trying to keep it clean for the Gibson guitars, which had, of course, humbucking pickups. And the thing about everybody knows about humbuckers is they have a higher output, and if they're trying to keep it clean with the humbuckers, you're really robbing a lot of tone. You have to take out a lot of frequencies in order to keep those clean most of the way up the dial. A coupling capacitor, its main job is to block the high voltage DC that is on the plate of the previous stage, so that you can safely couple to the next stage. But if we look at this, okay, so watch this voltage right here. So we've got, here's on one side of that capacitor, 194 volts right there at the plate of that stage. Now, through this coupling capacitor on the other side of it, you would expect to see almost no voltage, because its job is to block all of that DC voltage. The only thing you should really have over here is AC voltage from the guitar signal itself that passes through. This is supposed to block it, but look, if we come over here to the other side of it, look at that. We've got 12 volts of bias on that grid of that output tube. You don't want 12 positive volts. If anything, you want close to 0. So, and look over here on this one. So the one side of that should be right here. 171 volts right there on the plate side. But look at this, 10.4 volts is passing through those. So those are not good capacitors. This one right here, we've got 112 volts on this side of this capacitor, and we've got about 8 volts on the other side of it, which probably shouldn't be there. I'll have to look at the schematic to see if it shouldn't be there, but I'm pretty sure it should not. Then over here we've got 144 volts on that side of that capacitor, and then we've got 66 volts on the other side of that capacitor. So lots of things going on here that really should not be going on. So, you know, these capacitors are going to have to go. Those bumblebees for sure, and these right here I'm going to go ahead and replace as a matter of course. The Black Beauties usually aren't as bad as the bumblebees, but they're not good capacitors, man. You know, everybody's raves over these like there's some kind of magic bullet for tone, but they're really not. The problem is you've got an amplifier here that's operating well outside of where it should be. The main reason for that is these components are just starting to go bad. But I want to show you what the amp is doing at this particular moment. This is completely cranked. On the verge of squealing, so it's almost going into an oscillation of sorts there. You really notice that when you turn down the guitar, there's a little bit of squealing there. I don't know if you're gonna be able to hear that. Probably just a high-pitched squeal. You can back the volume off and get rid of that. So it's going into oscillation at the top of the volume pot range, and rather than changing the volume pot back to the 500K, which lowers that resistance pretty significantly, I think the best thing to do is to come back over here and change the value of that bypass capacitor on the first stage. Lowering the value of that bypass cap and possibly lowering the value of the coupling cap is going to help this amp a little bit. We might go to like a 0.01 coupling cap instead of a 0.02. Okay, so here we are. The amp is completely done, completely serviced. I'll show you what everything looks like here. You can see the modifications done. The first stage, of course, we've already talked about that. I did settle upon a 0.01 microfarad capacitor for the first coupling capacitor. Then it comes through a 1 meg pot. I have also this first stage bypass with a 2.2 microfarad bypass cap instead of a 22, which is a vast reduction. And the reason for this reduction is because the amount of gain coming out of this stage was really too much for the amp with that 1 meg volume there. So we modified that to accommodate a 1 meg volume pot, 0.01 coupling cap. To the next stage, coming out of the next stage, I changed this value right here, which was a 0047. It is now a 0.01 as well, into the next stage. Let's see. The rest of these are the same values, but I changed them. So obviously they are biasing the output tubes properly now. So instead of the, what was it, 12 volts roughly that we were seeing right there, on this side of this capacitor right here, look, now we've got almost nothing in terms of voltage, whereas before we had 12 volts right there. So right here we should have also likewise almost nothing, and we do. And that's the mark of a good capacitor. You leave those old capacitors in there, you think, oh man, these are the mojo, these are the business. Well, no, those aren't the business, because it's just preventing the amp from functioning the way it needs to function. So also went ahead and soldered that little terminal back onto the back of that new potentiometer. When I changed the power capacitors, I also changed the dropping resistor to a metal film dropping resistor, which is just going to hold up a lot better over time. It holds up better to heat. Check this out now. This is just with the speaker out on the desk. Okay, so one more modification that we're going to do. We're going to clean up the face a little bit also before we put everything back together and send it back. But we're going to drill a hole in the chassis. It's going to be a really discreet hole. You'll never see it. So it's in the back, but it'll be right about here. We're going to drill a hole, put a jack in for this output so that we can plug and unplug this speaker, and we can put an external speaker plugged into this, which is going to give him way more flexibility. And with this amp sounding really as good as it does, that will be a massive thing to have around a studio. I mean, this thing sounds phenomenal, really. So these wires that went to the speaker, we're going to run those back up through this hole. Okay, here's the part where we make all of the corrections to our schematic. This is the schematic that came out of the Gibson Master Service Manual. Has a 100K resistance here. The EA50T, which is the closest Epiphone equivalent, has a 68K. We actually do have a 68K in this amp, so the Skylark has, this Skylark at least, has a 68K for both of these values. We changed this value from a 1.5K to 750 ohms. We changed the 20 microfarad bypass capacitor right here to a 2.2. This value was not present. It was actually this, which is one of the tone-sucking networks, and into that tone-sucking network there was a 0047. We got rid of the 0047, got rid of the tone-sucking network, and replaced it with not a 0.02 as we see on this schematic, but we replaced it with a 0.01. This 500K pot we actually replaced with a 1 meg. We didn't mess with the biasing of the second stage, although we probably could have. We could have come in here and maybe even squeezed a little bit more out of the second stage and bypassed it with a small cap and gotten even more out of this amp. But we'll look at it and see. That might be something we come back in and do, but for now we're just going to leave it alone. This also, I believe, had and it did, yes, there was a 100K resistor as a grid stopper into the next stage. You can see it. It's present right here on this schematic, this 100K grid stopper into this stage. And you can see here, actually, they have it bypassed on this as well with a 0.1 and a 2.2K. And actually, no, I'll take that back. In the amp itself, there is a bypass capacitor right there of 0.1. So that already is in the amp. So they read my mind on that. They read my mind 50 years ago. So let's go ahead and notate that. So this actually does have a bypass cap of, what I say, 0.1. And again, there is a 100K resistor right there in the grid. Coming off of the plate, let me see what we have coming off of the plate of this thing. We have, this will be the second stage. It looks like we have two different plate resistors. They're in series for a total of about 100K. This amp looks like it just simply has it doesn't have two plate resistors. It just has this, we can get rid of this. So that is just straight across. Nothing there. This one, though, is like I said, is a 100K. This value is not 250 microfarads. We replaced that, what was in here, with, I believe it was a 0047 microfarad. So it would have been a 470 microfarad. So this one we replaced with a 0.01, also just like this first stage. Here we have a 470K resistor as a ground reference. We probably could have fiddled with that and upped that value slightly as well and pushed a little more out of this. I mean, this thing really, really rocks the way it is. So I don't think that's going to be necessary. So we'll probably leave that as is. So this is all correct right here. We should have a 0.01 off of that, and we do. Let's see. On the other side, I know we have a 0.01 because we changed that. We should have 100K coming into that right there, which we do. We should have a 220. Okay, so what happens here is there is a 0.01 and then a 22 and then this 220K. So this is in a different spot. This right here, I don't think it matters, but that resistor is actually right here before this 220. Probably is the same on the other side, I'm guessing. This side is notated correctly here. This side is not notated correctly. This side, they have the 22K moved back over here. So it is different, but I don't know that it makes that big of a difference to really worry about. I'm not going to go through the tremolo. I assume most of that's probably as notated on the schematic. We did remove the death cap and rewired the primary side. So we got rid of that. One more thing I want to note on here is that this first 0.01 in my usual fashion is a ceramic. It definitely makes a difference. It makes a difference in the way the amp responds. Another cool thing, one other thing that I did not note, there's a 0.0047. Is that right? Or is it a 0.0022 capacitor across the primary of the output transformer, which is consistent with the EA50. So that is right there, but it's not shown on the Skylark, but it is there in this example. I'll show you. And it is a ceramic capacitor as well. Right. This guy. So what is that? What value is that? That's a 0022 right there, going across the output leads. So we'll go ahead and annotate that. If it had not had it, I may have added something similar. I typically do add Zobel networks in amps that I modify, and that is kind of like a Zobel network. That's a .0022 capacitor across the output leads. So I hope that all makes sense. If you want to try your hand at modifying one of these, this is the schematic that, at least for now, I recommend. And oh yeah, the other thing I did was change this to a jack, but you get the idea. So actually we can, there we go. And it's a grounded jack, so. All right, so that's it. Let's give it a test.